and welcome to this sixth lecture on our course on blockchain and its applications. It is also the fourth lecture on the topic of basic cryptographic primitives that we have been discussing in the last few lectures. So, today we will be covering the concepts where we will introduce very basic ideas about cryptography, the different types of cryptography that are popular and which have a lot of different applications. We will have a little bit of more focus on public key cryptography, which indeed is more commonly used in the context of blockchains. We will see how and what is meant by encryption and decryption using public key cryptography. So, of course, we will first understand what is meant by encryption, what is meant by decryption, and then we will talk about digital signature. So, today's lecture will briefly mention about digital signature and we will see about its more details in our next lecture. The main keywords for today's lecture are public key cryptography and RSA, which is a type of public key cryptography and which is easy to understand from an application point of view, how we can make use of it in the context of blockchains. So, these are the two keywords that we will have in today's lecture. But before we do that, let us do a quick recap of what we have learned so far in this topic on basic cryptographic primitives. So, if we remember that we have talked about what are called cryptographically secure hash functions, and what was the property? The property was that these are irreversible functions. From a given message, I apply a hash function h, I get hm, which is called the digest, and it has got certain properties like it is collision free and information hiding can be done, and it is puzzle friendly. If you remember, we talked about use of these nonce to put certain restrictions on the values of the hashes, that is the digests of the messages like number of leading zeros, and we have seen that ensuring that the resulting hash follows these restrictions is not very easy computationally, and that property can be used to connect different blocks of data using hash pointers and eventually form what is called blockchains. So, that is what we have seen in the very last lecture, where we talked about hash pointers and the data structures, the corresponding data structures for the blocks. We talked about this Merkle tree also, which showed how we can represent hashes of various transactional data and then create hashes of those hashes and then further levels of hashes of the lower layers, so that we can have again finally at the root of the Merkle tree what is called a root hash. And then you see that if any one of the data below are changed, including the transactional data or any one of the hashes in between, then we have to go all the way up to ensure that till the Merkle root, which has the root hash, all of such hashes will have to be recomputed, and each of these recomputations, if it is computationally expensive because of the restrictions like number of leading zeros, it will become not so easy for an attacker to do so computationally. So, that is what we have studied so far. So, today's lecture is going to deviate from this notion of hash functions, which we have so far discussed and now we have completed. So, we will look into now more details about cryptography. Okay. So, some basic concepts of cryptography. So, broadly we can classify cryptography into two types. One is what is called symmetric key cryptography, the other is what is called asymmetric key cryptography or public key cryptography. And there are certain other terms that are also used to refer to these two different types of cryptography. Now, what is cryptography? Cryptography is very simple, that there is some message and then one party wants to send it to another party, and in the process of sending it, maybe over a communication channel which need not be secure, there could be some intruders trying to see what is happening or trying to change what is being transferred from the source to the destination. And then even in spite of having those types of potential adversaries who can attempt to make certain changes to the data or read the data that is being transferred from say the source which is say A to the destination which is B. So, how we can ensure that the data is sent in a so called quote unquote secure manner, and that is done by the help of cryptography. Now, the two broad steps, of course, there are other steps which we will discuss later in cryptography is what is called encryption of the data. So, if I want to send data D from A to B, I will not send the data D as it is, that means what you call it, it will not be sent in plain text. Instead, we will encrypt the data, means we will change the data in a such a way that the text that will be transferred will not be the plain text, rather it will be what is called the cipher text. So, the cipher text corresponding to the plain text will actually go from A to B, and this cipher text will be such that any adversary who can see what is that cipher text cannot figure out what is the plain text, but the receiver, the intended receiver from the cipher text will easily be able to come up with or get back to what was the original plain text. So, the terms that we have so far used, one is plain text, which is the message that is to be sent from A to B. We have this notion of cryptography. So, first step is that for A to send it to B, instead of sending the plain text, A will encrypt the plain text to generate a cipher text. The cipher text is the one that will be sent from A to B. B will be receiving the cipher text and will be able to get back to the original plain text, because that is what was intended to be sent by A to B, but it is being sent in a secure manner. Any adversary who can read that cipher text that is being transferred from A to B, this transfer could be happening in some unsecured channel where adversaries can snoop in. So, we would expect that the adversary first of all will not know what is the plain text by only looking at the cipher text. Also, the adversary will not be able to change the cipher text in such a way that it reaches B, and then when B decrypts it, B will end up reading something which was not exactly the one that was sent by A. So, B gets some plain text, but that is not what was sent by A. So, B should be able to detect whether there was any tampering that happened in between. So, the final step is from plain text, encryption, cipher text, then the intended recipient will decrypt the data, that is converting the cipher text back to the plain text, and then the side B will be able to make use of the plain text for whatever purpose. So, we have to ensure that while transferring the data, we are encrypting and it can be decrypted, and it should be done in such a way that in between any adversary will not be able to read that and also will not be able to change it. So, these are the overall requirements. Now, how do we generate this cipher text from the plain text and how we get back the plain text from the cipher text? So, these are the two steps which are of course are called encryption and decryption. So, how do I do that? Remember, you might wonder that, oh, I will use hash function and from the plain text I will hash, I will get some cipher text and that I will transfer, nobody will be able to get back, I mean the adversary will not be able to get back the plain text from the cipher text. We have discussed that in detail, but of course, you see that even the intended recipient also will not be able to get back the plain text from the cipher text. Okay. So, hash functions are not going to solve this problem, and that is being solved by this notion of cryptography here, which is going to use what are called keys. Okay. So, these keys are used for encryption and also for decryption. Now, in symmetric key cryptography, if we see that in symmetric key what happens is that the same key is used for encryption and also for decryption. Okay. So, if there is a key K1, then K1 will be used on the plain text to get back the ciphertext or to arrive at the ciphertext, and at the recipient end it is the same key K1 that will be used to get back the plain text from the ciphertext. Okay. So, that is what makes it symmetric, means it is the same key which is used for both encryption as well as decryption. In contrast, in public key cryptography, one key is used for encryption, while another one, a different one, is used for decryption. We will see that there are many advantages of this, but that was the basic definition between symmetric key cryptography and public key cryptography, and based on that we understand that for symmetric key it is the same key, and for public key cryptography we have one key which is for encryption and there is another key which is used for decryption. So, if we call this as K and K prime and say K is used for encryption, then K prime will be used for decryption, and we will see other properties also. Coming back to symmetric key, that one of the challenges is how do we share the keys securely, because it is the same key that will be used for encryption and decryption. So, sending the key itself has to be done in a secure manner, so that the two parties know which key is being used for encryption and also for decryption. And it cannot address certain requirements which can be actually handled by this public key cryptography, like in applications for example blockchain, as we have been talking about. So, we will see what is the importance of public key cryptography. So, now on we are going to focus on public key cryptography, because that actually handles many of the requirements that are there in the context of blockchains. So, from now on our discussion will be on public key cryptography. So, let us move on to the next slide, which is on public key cryptography, and here we will see that public key cryptography can be used for two purposes, and in the very first application of public key cryptography in blockchains will be for digital signatures. Now, what is a digital signature? A digital signature is a digital code that can be included with an electronically transmitted document, and it is used to verify that the content of the document is authenticated, the identity of the sender, and prevent what is called non-repudiation. Non-repudiation means the sender will not be able to deny about the origin of the document. So, this digital signature is one application of public key cryptography. So, what it does is that, say a document is being transmitted from A to B. So, when B receives it, then as I had mentioned that B should be convinced that it was indeed sent by A. That means, in between while transmitting from A to B, if there was an adversary who changed this message from M to M prime, then B would be able to detect that. Okay. So, that is important. The second is that the content is authenticated, means it was indeed sent by A. There was no way that anybody else could have sent it. Okay. So, the identity of the sender will be ascertained by means of this public key cryptography. We will see how to do it, and also once B gets it, it will show that it has been sent by A. So, later on A cannot deny that I did not send it. That is very important in many situations. So, if somebody says I am transferring this money to you from A is transferring money to B, and later on A cannot say, oh, I did not send the money. So, that is an example of non-repudiation. So, we will see how digital signatures that employ public key cryptography can provide these types of features. What is the purpose? So, only the signing authority can sign a document. So, just as any physical signature, then the signing authority can sign the document. So, if I am supposed to issue you a check, then I am supposed to sign the check, right. So, that is what we mean by the signing authority can sign the document, but everyone can verify the signature. So, as you can see that my check, once I have presented the check or I have handed it over to somebody else who is presenting the check to the bank, in that case the bank people can always verify the signature. So, and it is open for everybody to verify. So, only I can sign, but everybody can verify it that it is indeed my signature. Of course, people will have to know my original signature. That is why in the bank they have my signature kept in their records, okay. And also it is associated with the particular document, okay. It is not for any document. If I have signed check number 1, so that does not mean all checks can now replicate my signature and then they become valid. So, that is not possible. And similarly for digital signatures also, which are something equivalent to our physical signatures. So, signature of one document also cannot be transferred. Remember that it cannot be transferred to another document. So, this is also very important. So, we will see how to do that, but in order to be able to understand how digital signature works, what we will do is that we will first talk about public key cryptography. So, we will see that how digital signatures can be generated by making use of public key cryptography. So, we have mentioned that it is also called asymmetrical cryptography or asymmetric key cryptography. What is a key? So, key is a parameter that determines the functional output of a cryptographic algorithm, okay. And then this, as we mentioned, the encryption, the key is used to convert a plain text to a cipher text, as we mentioned before. So, that is the process of encryption, and decryption, that the key is used to convert the cipher text to the original plain text by doing the decryption function. Remember that in this case we have deliberately we have mentioned the same k both here and here, just to show that this is the basic definition of encryption and decryption, okay. But this k here and this k here, these two need not be the same, and indeed for public key cryptography these two are not the same, okay. So, this is k as is already written here, this is going to be something else, say k prime, as we discussed in our last slide, last couple of slides. So, that means that this is to say that there is a key for encryption and there is a key for decryption, but these two keys will be different for public key cryptography, as we will see very quickly. Okay. So, the properties of a cryptographic key is that the key should be generated truly randomly, so that the attacker cannot simply guess it. Like passwords also, we know that it should be random, so that an attacker cannot easily guess it. Similarly, the public key cryptography, for that the key should be generated randomly for an attacker to be almost impossible or very difficult to make a guess of it, okay. And it should be of sufficient length. So, this is also very important, that if the key is of shorter length, then somebody can keep trying in what we call a brute force manner, one by one all the possibilities can be tried and one can get the data back. Because if you see that for an attacker to get the data from the cipher text, that means getting the plain text from the cipher text, the key is required, otherwise the attacker cannot get back the plain text. So, the attacker, if it tries to get the key, then because the key will not be known to the attacker can only try to guess it, okay. So, the key first of all should be random, which is the first point as we mentioned, and also it should be of sufficient length, otherwise the attacker could keep trying, say the value of key as 1, then 2, 3, 4, if it is only of 2 digits, can only try from 0 to 99, and then one of them will cause the plain text to be generated back from the cipher text. Just as for password, we know that we have to set passwords of sufficiently large length, so that an attacker cannot easily guess it, okay. And there should be sufficient entropy, that means that all the bits of the key should be equally random. That means that typically if we consider these keys to be binary digit strings, that is bit strings, then it should not be a case that always it starts with 1. Then that means that the attacker will first choose 1 and then try out the combinations, or the first and the last one should not be 1. So, there should be sufficient such variations in the different bits, and that is what causes higher entropy in the key. So, all the bits in the key should be equally random. So, these are some of the important properties that we need to have our public key cryptographic keys to satisfy. As mentioned, that there are two keys which are used in public key cryptography, and one of them now it is called the private key. So, this term is important, that say for exchanging messages, each party, say Alice and Bob. So, we denote these parties usually in cryptographic term as two persons, we name them as maybe Alice, Bob and others. So, when there are two parties, we denote them as Alice and Bob. So, here we have Alice on the left and Bob on the right, and then each of Alice and Bob will have a pair of keys. Okay. So, for example, Alice will have a private key and Alice also will have a public key. Similarly, Bob will have a public key, Bob will also have a private key. What is a private key and what is a public key and what is the difference? So, say for Alice, her private key will be known only to Alice. So, only Alice has her private key, and the public key is what we call public to everyone. That means, everybody would know Alice's public key. So, if Alice generates this public key private key pair, then Alice will keep the private key with herself and make the whole world know about the public key. Likewise, if Bob generates a public key private key pair, Bob will keep the private key to himself and will let the entire world know about the public key. And then if data is now to be sent from Alice to Bob, and remember here yet we are not talking about digital signatures. We are talking about sending data securely from Alice to Bob, so that if there is any adversary here, the adversary will not be able to figure out what message was being sent. So, in that context now we are talking about this public key cryptography. So, this is for encrypting the data from Alice to Bob, so that an adversary in between cannot read what was sent by Alice. It is not talking yet about digital signatures, that should be very clear. So, in order for Alice to send a message M to Bob, what Alice does is that Alice encrypts this message with Bob's public key. So, K superscript B and then subscript pub, it denotes that B denotes it is Bob's key and pub denotes it is the public key. So, we represent this encryption process as this tuple, the message comma, then which key is used for encrypting it, and doing that we get this M prime. This M prime is the ciphertext. So, the M prime is the ciphertext. So, this is spelled as CIPHER and sometimes CYPHER, but they mean the same. So, what we have is that we have this M prime as a ciphertext, and this M prime is what is being transmitted over an unreliable link, or unreliable means non-secure link, I would say, from Alice to Bob. So, if there is an adversary here, adversary cannot get back M from M prime. How can one get back M from M prime? It can be done only by decryption using the function D, and for that it takes as input this ciphertext M prime, and also it uses the key which is now the private key of Bob. So, if you see, it is K B superscript and pri as the subscript. Okay. Now, who knows the private key of Bob? It is only Bob who knows the private key, and using that private key and M prime, this tuple as input and applying the decryption function, Bob can get back the message M, which is the plain text. The adversary who had access to M prime, but no access to the private key of Bob, will never be able to get back what was the message that was being sent, that is this M that was being sent from Alice to Bob, but Bob can get it back from the M prime. So, that is how basic function of encryption and decryption works, which ensures confidentiality of the data as it moves from Alice to Bob. That means, no other adversary in between will be able to get the original data back from the ciphertext. That means, will not be able to get back the plain text from the ciphertext. Now, there are many ways of doing this public key cryptography, of which one of the pioneering work was that called that by Rivest, Shamir and Adelman, and that is what is called the RSA algorithm. And the encryption key is public. So, that public key is the encryption key, and the decryption key, which is the private key, that will be kept secret, and anyone can encrypt data. So, that means that it was Alice who was sending to Bob, but instead if Tom wants to send it to Bob, Tom will be now using again the public key of Bob to send the data. Because this public key is to everybody, Alice, Tom or anyone can encrypt any data with Bob's public key and then send it to Bob, and Bob will be always be able to get the data through decryption, whether it was sent by Alice, whether it is sent by Tom, because whoever is sending it will be sending it by encrypting the data using the public key of Bob. So, the RSA algorithm, so there are basically there are 4 broad steps. One is the first of all, it starts with generation of the key. So, the key pair has to be generated. Key distribution, meaning the public key has to be made known to everybody. Of course, the private key will be secret with the party who is generating the key, like say Alice or Bob, and then of course, encryption of the data while sending the data, and then the recipient will be receiving the data by doing the decryption with the private key. So, as we have seen before, from plain text by applying the public key we get the ciphertext, and from ciphertext by applying the private key we get the plain text. And this is the interesting property of RSA and in general for public key cryptography, is that if I encrypt any text with the public key, I get ciphertext. If I decrypt it with the private key, I get back the plain text. Likewise, if I encrypt a plain text with the private key, I will get back a ciphertext, and then from that ciphertext, if I use decryption with the public key, I will get back the plain text. And this second property that I have said, that is the one that will be used for digital signature, which we will study later. So, now this generation of public and private keys in RSA. So, it is these are the some of the steps, and these are for the sake of completeness. Actually, for our understanding of how public key cryptography is used for digital signature will not require you to understand all the detailed steps, but here is a brief overview of the detailed steps that are also available in the book by Stallings. So, it is feasible to find 3 very large positive integers. One is E, the other we denote as D and N, and it needs some modular exponentiation operations for integers m, where 0, m and n, that m raised to the power E raised to the power D is congruent to m in modulo n operation. Okay. That means that m raised to the power E raised to the power D, if we divide by D, then we end up in the remainder of m. So, the property is that even if you know E, n and m, it is very difficult to find D. So, that is the property that we need to satisfy, and also just as we had m raised to the power E raised to the power D is congruent to m mod m, but m raised to the power D raised to the power D, we could write it as m raised to the power D raised to the power E, then that would also be congruent to m mod n. That means that if E n is used as the public key, and then we can use D n as the private key, and m denotes the message that needs to be encrypted. So, if an message m has to be encrypted, then what we have to do is that we have to do this first step of encryption, and then whatever is obtained as the output, that will be used for decryption using the decryption key. So, RSA key generation and distribution. So, what are the steps? As I said that these are for the sake of completeness we are discussing. We are not going into the detailed mathematics behind it, which is not required for understanding how it works in the context of blockchain. So, basically two distinct prime integers p and q are first chosen, and then they are to be chosen at random to ensure high security. These are at random. Then the steps are easy, that we compute n equal to p into q, where this n will be used as the modulus which we discussed in the last slide, and the length of n is called the length of the key or the key length. And then we compute phi n, which is called the Euler's totient function, by computing this p minus n multiplied by q minus n, which is very easy. And then an integer e is to be chosen such that e is greater than 1, but less than this value of phi n, and GCD of e and phi n is 1, meaning that e and phi n, these are co-prime. That means there is no common factor. And then we determine d, which should be congruent to inverse modulus phi n, and d is the modular multiplicative inverse of e in modular phi n operation. And it is to be noted that d and e are such that d multiplied e is congruent to 1 mod phi n. That means that if d into e is divided by mod phi n, it is divided by phi n, I am sorry. So, then it will result in 1. So, that is meant by d dot e is congruent to 1 mod phi n. So, these are the basic steps for RSA key generation, and once these are generated, then the key are to be distributed. So, that was the key generation step. I am sorry that it moved forward a little too fast. So, basically some very common and well known steps are used for generation of the RSA keys, the encryption key and the decryption key. Once generated, these are the encryption key is known to everybody, which is basically the public key, and the decryption key is the private key, which will be known only to the person who is generating this key pair. So, to conclude today's lecture, we have discussed the very basic concepts of public key cryptography. We have tried to see what are the properties it must satisfy. Of course, we put it in the context of overall notion of cryptography and what is symmetric key and how public key cryptography is different from symmetric key cryptography. And then we have seen how to generate keys in RSA, and also as we will see in our next lecture, that we need not really worry about doing all those steps that we showed in the previous slides like these, that how to generate the keys. There are ample libraries in any programming language which will generate the keys for you. There are websites, as we will see in our next class, where you can generate key pairs and make use of those. But we have seen what are the underlying steps for generating these encryption and decryption keys for RSA. So, that brings us to the end of today's lecture, and these details that we talked about for the generation of keys for RSA and basic concepts of cryptography, of symmetric key cryptography and public key cryptography, all these you can get from this book, and there are many other such excellent books, and we have excellent lectures, online lectures also on cryptography, which you can always refer to. And we will try to keep the properties of public key cryptography in mind for our subsequent discussions in the context of blockchain. So, with that we come to the end of today's lecture. Thank you very much for your attention.